Good afternoon, everyone, and I would like to thank Michele and the other organizers of this discussion group for their kind invitation. They asked me to talk today about one of our recent works, which is related with the long-range screening and interatomic force constants that are relevant to the calculation of phonons in 2D materials. And that's what I will be doing in the second part of my talk. But first, I will perform a sort of long introduction to the topic of this long-range electrostatic stuff, which will be focusing more into the 3D systems with a couple of our contributions also on this side. Okay, as I said, this talk is going to be about phonons, and in particular about how to calculate and interpolate phonon band structures from first principles. And why one should be interested in calculating phonons? Well, phonons, as you probably know, can be considered as a sort of fingerprint of a material that can be calculated theoretically, but also experimentally measured, and serves for the structural characterization of different materials. Besides, the theoretically calculated phonons can be used to monitorize the appearance of instabilities by means of this kind of imaginary frequencies, and also by integrating the phonon frequencies and polarizations over the Brillouin zone, we can have access to thermodynamic properties such as the specific heat or the thermal conductivity. Besides, phonons also influence other properties of the materials by means of their scattering with other quasi-particles, such as the electron mobility by means of the electron-phonon coupling, and they also influence, for example, optical properties. The point is that to calculate, for example, thermodynamic properties, one needs to have a fast access to these phonon frequencies, not only at few points of the Brillouin zone, but to reach convergence on the final properties, one has to calculate the phonons at many points in the Brillouin zone, which means that it is important to have an efficient approach to calculate the phonons. So formally, the phonon frequencies and polarizations are obtained from the eigenvalues and eigenvectors of the dynamical matrix, which in turn can be calculated from the force constant matrix by applying this mass-dependent term. The force constant matrix is going to be the main object of my presentation, and it can be defined as the second-order derivative of the total energy with respect to the displacement of two atoms from their equilibrium positions. All along this presentation, I will be using this notation where this kappa and kappa prime subscripts describe sublattice indices. Another set of Greek letters are used for Cartesian direction, except tau, which I will use to illustrate the atomic displacement or so-called phonon perturbation. Okay, nowadays the most accurate force constants can be calculated from first principles via density functional perturbation theory, which allows the calculation of these forces at any Q point, regardless of the commensurate character of this Q point with respect to the simulation cell employed for the calculation. However, in spite of this capability of the DFPT formalism, in the practice, these forces are not calculated all over the Brillouin zone. They are normally only exactly computed at a set of points that form a grid in this Brillouin zone, and in the rest of the zones, of the points of the Brillouin zone, they are rather interpolated. And it is well known that for the case of polar insulators and semiconductors, for this interpolation procedure to work properly, it is important to separately treat the short-range and long-range force constants. And let me show you an example of how this interpolation approach works. As I said, one typically starts from a set of force constants calculated over a quartz grid of Q points. Here in the example, a 4x4 grid of Q points. And then one defines a long-range force constant matrix, which is typically obtained from the electrostatics of the system, and subtract this long-range part from the calculated force constants. The remainder is a set of short-range force constants in reciprocal space. In the next step, what one does is to Fourier transform these forces into real space to obtain the real space representation of the force constancies over a supercell that is dual to the initial grid of Q points in the calculation. The final step consists in backwards Fourier transform these real space force constants into momentum space at any arbitrary Q point. And then the long range forces are added back to these interpolated forces to recover the total force constant matrix at any arbitrary Q point. As you can see, this is simply a Fourier interpolation approach, but it becomes crucial to have a physically valid way of defining these long range force constants and also an efficient way of calculating them, because we will have to calculate them at many Q points. We do not interpolate these force constants. So my talk is going to be mostly on how we can define these long range force constancies and how we can separate them from the short range part. But let me start from the very beginning by reasoning why these force constancies have a long range character. And to this end, I will use the dielectric matrix formalism that was employed in this classic paper of the 70s by Pick, Cohen and Martin, which was one of the pioneering papers of the lattice dynamics calculation from first principles. And in this manuscript, the force constants were represented as the product of three quantities. Two of them are the bare point dipoles induced by displacing the nuclei from their equilibrium position. And then this W is where all the complexities of the electron-electron interactions live, and it is the so-called screened Coulomb interaction. One of the main results of this paper was to be able to demonstrate that the long-range character of the force constants was originated in the non-analytic behavior of this W screened Coulomb interaction at small values of the wave vector Q. So in order to show you more into the detail of where this problem is, let me write down here the formula for this screened Coulomb interaction. This is a two-body operator acting on R and R prime, that here it's written in terms of two other quantities. One of them is the bare Coulomb kernel, 1 over R operator, and the other is the so-called irreducible polarizability, which describes the charge response of the system to a screened potential. And it can be calculated with this Dyson equation in which the electrons only interact via the exchange and correlation kernel. Then within the LDA or the semi-local approximations of the DFT, this irreducible polarizability is an analytic function of the momentum, which means that all the non-analyticities of the W operator are included in the Coulomb kernel. And this is precisely the body on which we need to act in order to perform this separation between short range and long range. So the idea is to write a short range part which is completely analytic, and it includes the local fields, and it is typically a big operator that describes the response of the electrons on an external electric field, but on a microscopic length scale. And another part, which is the long range one, that includes all the non-analyticities of the total kernel, and it hopefully lives in a much smaller space than the short range part. If one is able to reach this separation for the Coulomb kernel, this immediately leads to an exact separation also for the force constant matrix, in such a way that we can write this formula for the long range part of the force constancies, which is quite similar to the one that I showed a couple of slides before for the total force constants, but with the main difference that here now what we have is the long range Coulomb kernel, which, as I said, is much smaller, and it makes this quantity easier to calculate. The other material dependent parameters that are here colored, and also the short range force constancies, in principle can be calculated from density functional perturbation theory as second order derivatives of the total energy with respect to two perturbations, the phonon perturbation and a scalar potential perturbation. But since they are short range in character, in that calculation, the self-consistent kernel should be also short range, which includes the exchange correlation kernel and only the short range part of the Coulomb. Let me remark again that among all these quantities, the only one that is non-analytic is the Coulomb, the long range part of the Coulomb kernel. So up to here, I have kept the formalism quite general, but now let's focus on the three-dimensional case. And our goal is to find a formula to calculate these long-range force constancies. So let's start from separating the short-range and long-range Coulomb interactions. This is a trivial process in 3D, because if we take a look at the reciprocal space representation of the Coulomb kernel in 3D, we see how the only non-analytic component of the Coulomb kernel is the G equal 0 term. Therefore, the separation is quite easy. One takes only the G equal 0 term for the long range part and the rest of them for the short range. And this also means that our long range potentials in 3D will be macroscopic potentials. Then the remaining ingredients here were this charge response to the displacement of the atoms and the polarizability function. That, as I said before, one could try to calculate them from DFPT calculations, but in practice, this involves several technical complexities whose discussion I think is beyond the scope of this talk. So I will discuss instead the traditional approach, which is to take the Taylor expansion of these quantities in the momentum around the Q equals 0 point and cutting this expansion at first order, which leads to these well-known macroscopic properties of the materials. Here we have the Born effective charges, and here the macroscopic dielectric susceptibility. Finally, by combining these two ingredients and the long-range kernel in this formula, we can easily recover the famous dipole-dipole formula from Cochran and Cowley that was first phenomenologically demonstrated and later on put it on firmer grounds by Cohen and Martin by following this similar approach that I have used here. Well, this is the formula that is implemented in most electronic structure packages in order to interpolate long-range forces. And it describes, as I said, the interaction between two dipoles, and this interaction decays as the inverse of the third power of the distance between the atoms. So one of the things that we did was wonder if we could improve this approach by extending this expansion, this multipolar expansion up to the next order, which involves the appearance of the so-called dynamical quadrupoles. And why we were interested in the quadrupoles? Well, first of all, because we were able to calculate them thanks to our recent implementation of the long wave DFPT formalism that is already available in Avinit, that it was more devoted to the flexoelectric problem, but as a byproduct of the flexoelectric problem, we could also calculate these quantities, these dynamical quadrupoles. But also because these quadrupoles, we expected them to be important for the interpolation of phonons in piezoelectric materials. Because also Richard Martin, again in the 70s, demonstrated that the clamped-ion piezoelectric tensor can be written as a lattice summation of these dynamical quadrupoles. That today, 50 years after this, the presentation of this formula, we are able to calculate. So we did it, we incorporate these quadrupoles in interpolation formalism, and we applied to a prototypical piezoelectric and ferroelectric materials such as the rhombohedral phase of barium titanate. Here, what I'm showing is the phonon band structure of this material calculated with the standard dipole-dipole approach in red dashed curves and with our higher order interpolation approach in black. As you can see, the results are not very impressive. The two curves mostly overlap except for the regions near the gamma point, as we expected, because here is where the macroscopic electrostatics are important. And I want to point your attention to this region here, where the standard dipole-dipole approach leads to the appearance of this unphysical imaginary acoustic branch, which clearly disappears when we use our higher order interpolation approach. One could try to improve the result of the standard dipole-dipole approach by increasing the density of Q points that are initially used to perform the perturbation. But as you can see here at the left, this is an artifact that is not solved by reaching quite high densities of Q points. And the reason behind that is that this is not a problem directly related with phonon frequencies, but with acoustic, with sound velocities. The sound velocities in piezoelectrics are related with some macroscopic electric fields that are only captured by this lattice dynamic approach when you include the higher order multipoles in the formalism. And as you can see, for our approach, regardless of the initial grid of Q points, we always obtain physically valid frequencies, and we have already converged results with this quite coarse grid of 4x4x4 Q points. Okay, up to here, the 3D case, and the obvious question now is can we do the same for 2D materials? I anticipate that the answer to this question is yes, but the scenario is a bit more difficult. To illustrate that, what I'm showing here is for a 3-dimensional bulk crystal. The color scale is the charge density induced by a polar phonon, which is traveling along this direction Q. And these lines are used to illustrate the generated electric fields due to this phonon. And in 3D, the fields, as you can see, are only modulated along the longitudinal direction, because in the perpendicular one, we have the crystal periodicity. The situation in 2D is very different due to the high anisotropy of these systems, which are extended in the in-plane direction, but microscopic in the out-of-plane one, in such a way that all longitudinal phonons traveling in this direction will generate a set of non-uniform stray fields which decay into the vacuum following this exponential function. And here we already see how at very small values of Q, these stray fields will travel very long distances. Okay, there have been proposals to solve this problem at the first principles level and also at the interpolation of the force constant level, but they are based on two-dimensional dielectric models. And what we want to reach here is the same fundamental level of understanding that at that time was obtained by Cohen and Martin for the 3D case. So this will be mainly the focus of this second part of the seminar. Okay, first of all, let me try to illustrate you which is the problem of calculating phonons in 2D material with a 3-dimensional code. For example, imagine that I want to calculate the phonons of an hexagonal monolayer of boron nitride. For that, I can place this monolayer into a supercell with enough vacuum on top and below the monolayer, with the aim of having an isolated monolayer. But this is obviously replicated in the out-of-plane and in the in-plane directions. And then I try to simulate a phonon traveling with this in-plane wave vector. What I obtain in such a case is, for the case of the longitudinal optic phonon, is this red line, which, as you can see here, deviates near the gamma point quite considerably from the exact result that is here shown in black. And the reason for this artifact is precisely the stray fields that I was mentioning in the previous slide, that at very small values of Q, they spread into vacuum in such a way that there is a crosstalk between the the replicas of the monolayer, which leads to this kind of bulk-like rather than 2D-like dispersion of the LO phonon. There is an approach to solve this problem, which is the so-called Coulomb cutoff method. which basically cuts the tail of the Coulomb interaction in the out-of-plane direction, and in this way it eliminates the crosstalk between the images, the periodic images. It has been applied to the phonon problem by Sawyer, Calandra, and Maury, and it has been shown to work nicely for DFPT calculations. But how about our understanding of the long-range forces? How can we physically interpret these long-range forces in 2D? Okay, if we try to do this from the Coulomb cutoff approach, for example, by representing this Coulomb kernel in reciprocal space, it has this form, and we can try to follow what we did in the 3D case, to remove the g = 0 component and see if this is a small space quantity which includes all the non-analyticities. But what we find here is that this kernel, by the presence of this exponential function, becomes non-analytic not only non-analytic for a given g = 0 vector, but for a whole column of these gm vectors, which are the reciprocal space components components of the vectors in the out-of-plane direction, which is clearly not convenient for us, because that means that we will be working with quite large dielectric functions that will complicate everything. So to solve this problem, we used a different approach, which was based on the classical image charge approach that we can find in classical electrodynamics books. And it consists in substituting the electrostatics of the monolayer isolated in vacuum by a set of replicas of this monolayer with alternating sign. This system of the alternating sign replicas will be short range. Will have a short range electrostatics, because if we look it from enough far away, this will be like a neutral system, and therefore it will be short range. Then the long range part is defined as the remainder between the total potential of this isolated monolayer system and this other one. Okay, this might seem a bit exotic, but this sort of Coulomb kernel, this short range Coulomb kernel, can be already be employed with the existing electronic structure packages nowadays. To this end, it suffices to perform the same phonon calculation that I showed a couple of slides before, but in this case, instead of using an in-plane and completely in-plane wave vector to calculate the phonon dispersion, the component of the momentum in the out-of-plane direction lies in the zone boundary. And this introduces precisely a 180 degrees phase shift between the images that reproduces this alternating sync pattern. So if I go to one of these packages and calculate this dispersion of the LO phonon employing this trick, what I get now is this red line that, as you can see, is much better than the previous result. In particular, it is correct at the gamma point. And still we are missing something, of course, which is the long range part that we will define precisely as the difference between these two calculations, the exact one and this short range one. Okay, in practice, what we do is to start from this representation of the Coulomb kernel, which is in momentum space in the in-plane directions and in real space in the out-of-plane. And then we start to play this game of introducing the image charges with alternating signs until eventually we reach this easy formula for the long-range Coulomb kernel, which is written in terms of different ingredients. First, these phi functions are the equivalent of the scalar potential perturbation that in 3D is completely scalar, but here in 2D is clearly non-uniform along the out-of-plane direction. And it is mediated by this pair of hyperbolic functions. Then here we have the F function, which is a so-called range separation function, which plays the equivalent role as to the Gaussian functions in the equal summation techniques, and it includes this L parameter, which physically is the distance between our replicas, that tells us or tells the kernel what is short range and what is long range, and it's equivalent to the equal parameter again in the equal summations. This kernel also reproduces the well-known long wavelength limit of the Coulomb interactions in 2D, which is different than the one from 3D. Here we have the inverse of the first power of the momentum, whereas in 3D one has the second power at the denominator. Okay, I understand that this can be a bit difficult to follow if one doesn't show all the algebraic steps, but okay, the message here that I want you to keep is that in spite of the difficulties of the 2D systems with all the stray fields going into vacuum and so on, we have reached a quite easy formula which is only two-dimensional compared with a scalar problem that we have in 3D. And in this case, instead of having a scalar dielectric functions, we will have 2x2 dielectric matrices, which, however, are small enough for us to calculate them from first principles. Now, let me say a few words of why we end up with these hyperbolic functions. Of course, there is a mathematical justification for that. They appear constantly in 2D problems when you perform Fourier transforms. But what they do physically here? To show that, let's, for example, expand in Q the hyperbolic cosine, and what we see is that this is just, this is an even function with respect to a reflection with respect to the z equals 0 plane. And it mediates interactions between multipoles that are in plane. On the other hand, the hyperbolic sinus is clearly an odd function with respect to this reflection, and it mediates the interaction between out-of-plane multipoles, dipoles or quadrupoles and dipoles. And the interesting thing is that unless the material that we are studying breaks this inversion symmetry, there won't be crosstalk between these two subsystems. Well, at the end of the day, using this long-range representation of the Coulomb kernel and the same expansion of the charge density response and susceptibility response in a long wave or multipolar expansion, we arrive at this formula for the long-range force constancies in 2D, which, as I anticipated before, it has two separated parts that describe the interaction between mirror-even multipoles and between mirror-odd. The mirror-even part is consistent at the lowest order in Q, I mean at the dipole-dipole order, with the earlier treatments for the long-range force constancies, for example, the one from Soyer et al. But here we have an improved description of the dielectric constant because we have not assumed any model to describe this quantity. On the other hand, the mirror terms are new, and they are a consequence of our formalism and haven't been used before in the existing implementation. Finally, let me say also that this is an exact formula in the sense that it can be used at any order in Q that one wishes to keep this expansion. In our calculations and the result that I'm going to show you next, we have stopped at second order in Q, which corresponds to the dynamical quadrupoles. Okay, let's go for the results that we obtain. This is again for the hexagonal boron nitride monolayer. And here what I'm showing in these blue dots are the exact frequencies obtained with density functional perturbation theory calculations. Then in dashed, we have the state-of-the-art implementation of quantum espresso, which is based on the Soyer et al. Formalism. And in yellow, the results of our interpolation code. And as you can see, we obtain a not very impressive result here in this case, but we clearly have some improvement with respect to the dipole-dipole approach of Soyer et al. Although in this case, this improvement is not due to the quadrupoles, but to our better description of screening. The quadrupoles, in turn, are required in order to properly describe the long wave behavior of some extra diagonal elements of the force constant matrix. For example, here, this is the force constant matrix element that describes the interaction between these two phonon branches. And as you can see, it is very important to include the quadrupoles to correctly describe this, even qualitatively describe this behavior. And this is probably most interesting, and it regards the ZO phonon branch. The ZO phonon is an out of plane displacement pattern of the monolayer. And as you can see here, we clearly reproduce the linear dispersion that is also obtained in the exact DSPT calculations, which was not captured at all by the earlier approach, where this part that is precisely the mirror part that is new in our calculations was absent. Okay, with this I finished my presentation. I want just point you a few things. First of all, that the method that I have shown at the beginning of the talk, including dipole quadrupoles and quadrupole terms, is implemented in Abinit. It's already in the public version of the code. And the same will be true soon for the formalism to interpolate phonon bands in quasi 2D materials. But in this case, the implementation will be soon on quantum expression. Also, there are some implications for the interpolation of electron phonon scattering potentials. We have already reported the results of studies in these two papers, and if you are interested, you can take a look at them. And we are now working on a similar study, but in the case of 2D materials. And that's all. Thank you for your attention.